Hello, this is Mrs. Nearing, and we're going to go over the problems on the backside of the polyprotic acid practice. Okay, and so problem number one, write the chemical equation and equilibrium expressions for each of the three ionization steps of phosphoric acid. And I realized I didn't give you the formula for phosphoric acid, so let's think about our naming rules. So we know if it's an ic acid with no hydro in front, that's based on the 8 anion. So that means phosphoric acid is the acid based on the phosphate anion. And notice how phosphate has a -3 charge, meaning phosphoric acid is going to have 3 hydrogens there. So notice how this is a polyprotic acid because it has more than one ionizable hydrogen, otherwise known as a proton. And this specifically is called a triprotic acid because there's 3 of them. So you could be triprotic. In the case of H2CO3, it could be diprotic. And if you're something like HF, we would call this monoprotic. So different acids can have different numbers of hydrogen. Tri is typically as high as it goes. I don't know of any quadroprotic acids. Okay, so the key thing with these is we treat each ionization step separately. So H3PO4 doesn't lose all 3 hydrogens at once. We think of these as 3 different equilibrium expressions here. So first we lose 1 hydrogen, and that leaves behind H plus and HPO4 minus. Whoops, H2PO4 minus. And then that anion can go ahead and lose the second hydrogen. So now notice it's going to have a -2 charge. And then that anion can go and lose the third hydrogen. So it's starting with a -2 charge, loses 1 more hydrogen, so now it's got a -3 charge here at the end. Okay, and each of these reactions are equilibrium reactions, and they each have their own K expressions. And since they're all Ka values, so they're all related to an acid, and they're all related to the same acid, we call them Ka1, Ka2, and Ka3. Okay, and the way we write a K expression is the same as always. Feel free to fast forward through this part because this will take me a little while, but it's always products over reactants. I'm using brackets because this is a Kc expression. Make sure you include charges when appropriate. H2PO4. And then I've got my last one here. And then we should be able to predict the magnitudes of these. So we will find that the value of Ka1 is always greater than Ka2, which is always greater than Ka3. And typically they're, Ka1's a lot bigger than the successive ones. And if you think about what's happening here, like in this first case, again, you are losing a hydrogen from a neutral molecule. Second step, you're losing a hydrogen for something that's negative. Third step, you're losing a hydrogen for something that's even more negative. So the more negative your initial thing is, the less likely it's going to want to lose another hydrogen. So these reactions become less favorable as you get more and more negative to begin with. And you can see down here with your K values, see how they get much lower. And notice, again, pay attention to this. We're talking about orders of magnitude here, right? So the Ka2 in this case is 10 to the 5th smaller than your original one. So that's like 5 orders of magnitude. So 10 times 10 times 10 times 10 times 10. It's much, much smaller, okay? So when we are finding the pH of a polyprotic acid, we usually just use this first ionization, and we assume that the second and third ionizations are very small relative to the initial, so they contribute an insignificant amount of hydrogen ions. Okay, so if we're trying to find the pH of this solution, we would just look at this first reaction because it has the largest Ka value, so it's gonna be the only one having a significant impact on my H plus concentration, and my initial value is 0.115 molar, and these start out at 0. And so we go through and fill in our, our ice chart here. There we go. Remember, an ice chart's just a way to organize information so we can plug it into our K expression. So our Ka1 is written up here. So if I plug it in there, it's going to be x squared 0.15 minus x, which you can simplify to x squared over 0.15 because my Ka value is, just barely 10 to the third smaller than my initial number. That's we're kind of pushing it here. But let's see, 7.5 times 10 to the negative third. And then we're going to go through and we're going to solve for x. So x would be the square root of 7.5 times 10 to the negative third times 0.15. And paying attention to what we labeled things, x is our hydrogen ion concentration, so the pH would be the negative log of x. So you'll be able to find the pH of that solution there. And again, we ignore the second and third ionizations because their K values are so much smaller. It's not going to really, it'll basically have an insignificant impact on our hydrogen ion concentration. Okay, so let's scroll, whoops, what happened there? Let's scroll down. Sorry about that. If we scroll down here a little bit, you could also find, this one might get a little bit trickier, but it's still just a nice short thing. You can also find concentrations of the other ions in the solution. So we can find the concentrations of H2PO4 minus, HPO4 minus, and PO4 3 minus. Okay, and basically what this means is, well, we already kind of found, let's look above. So HPO4 minus, do we know the concentration of it? Yeah, that actually is the same as X from the previous problem. See right here? This is the concentration of H2PO4 minus. So let's plug this in our calculators really quick, because we'll need this to go on. Times 0.15. Excuse me as I plug this in my calculator. So what I'm getting is 3.4 times 10 to the negative 2 molar. That's what I got for my X from above. Hopefully we are agreeing on that. So I found this, H2PO4 minus. Let's figure out the concentration of HPO4 minus 2. So where does that get made? That gets made in the second ionization. So H2PO4 minus is going to lose another hydrogen to make HPO4 2 minus. And then we would set up a nice chart. And then this is 3.4 times 10 to the negative 2. And then these start out at 0. So we go through and do our same old deal that we should be getting, really good at now. Minus x, x, x. Okay. And then I'm going to plug it in my Ka2 expression. So make sure you're using the right Ka value. I might just write this as 0.034. It makes it a little bit easier. And let's take a look at what our Ka2 value was. It looks like it was 6.2 times 10 to the negative 8th. Okay, 6.2 times 10 to the negative 8th. So if we go through here and we solve for x, it will give us the value of H2PO4 2 minus. All right, so that will give us this second value right here. And then we would go on and use that number and plug it into the third equilibrium. So HPO4 2 minus, it's going to make H plus, and PO4 3 minus. So you take this number right here, which you calculated, you can plug that in your calculator, and that would become your initial value in this third ice chart. Okay, and then we would do the whole thing, x plus x, so we would do our whole deal again, and we would solve for x, but we're using our Ka3 value. So it's going to be x squared over some value equals Ka3, which is going to be 4.2 times 10 to the negative 13. And when you solve for x in this case, x is going to equal your concentration of PO4 3 minus, if you look at how we defined it here. So you can go through all these steps and figure out the concentrations of all your ions. You should find them getting successively smaller, right? I would expect my concentration of phosphate ion to be very small because this Ka value is very small, and it should be smaller than this value, which will be smaller than our initial value of H2PO4 minus. You could also go through and look at your X value and see if it would have made a difference if you'd added this to your hydrogen ion concentration, whether that would have affected your pH or not. And you should find that it does not affect your pH because these numbers will be so much smaller than this value right here, the 0.034. So that's an overview of what to do with these polyprotic acids. There's a couple of more practice problems here on the bottom. So problem 4 and 5 and 6. So again, taking a look at 4 and 5, the key thing we should be thinking about is just use your Ka1 only, because the Ka1 is so much bigger than the second ionization, then you can ignore that second ionization. So you're basically treating these two problems as if they were just monoprotic acids. And you kind of just ignore this second value, because we can see that this second value, the second K value, is several orders of magnitude smaller than my initial K value. And then down here in problem 6 is a lot like problem number 3, in which case, except problem 3 we had to do like 3 ice charts. This one we only need 2 ice charts. So you would do, so first you would go through and you'd say, okay, H2CO3, it's going to lose 1 hydrogen, and then that anion is going to go through and lose a second hydrogen. And then, so what you do is first you go through and you solve an ice chart for my first equilibria using your Ka1, and then you would use the value you determined in that first step to set up another ice chart and use Ka2, and then you should be able to solve for your carbonate in that second equilibrium. So that's an overview of different kind of calculations you can do with polyprotic acids.